All right, guys, I'm going to talk to you a little bit today about momentum. You've all heard about momentum before, and you know a little bit about it, but we're going to define it as the property or tendency of a moving object to keep on moving. But mostly we're going to define it in terms of an equation. For some reason in physics, we use the symbol P to stand for momentum. So momentum is equal to something's mass times its velocity. So if we think about the units for that for a second, we tend to measure mass in kilograms, and we tend to measure velocity in meters per second. There's not a special name for that unit that I know of. That is the unit we're going to use for momentum, a kilogram times a meter over a second. Now that's a little bit different than what a newton is. It looks kind of like a newton, but remember, a newton is not mass times velocity. A newton is mass times acceleration. So that's going to be kilograms times meters per second square. So don't confuse the unit for momentum, which is this one, with the unit for force, which is that one. Now, momentum is related to Newton's second law. You guys all know that F equals ma. And you also know that acceleration is change in velocity over change in time. Newton actually first wrote his second law more like this than he did F equals ma. He wrote F equals m times change in velocity over change in time. But I think the original way he actually wrote it was he multiplied both sides by t. So he had this equation, F delta t equals m delta v. Now I want you to notice, and this is a really important idea, it's one of the biggest ideas in the momentum chapter that we're going to be dealing with. Over here on the right, m times change in velocity. Well, mass times velocity is momentum. So we call this side change in momentum. Well, this side over here is causing that change in momentum. It's equal to it. This side we call an impulse. And this equation is called the impulse momentum theory. It's essentially another way of writing Newton's second law. And it says if you apply a force over a time, that's going to cause a change in momentum. It's not going to change the mass, it's going to change the velocity. So that's impulse momentum theory. And it has a lot of applications. For example, let's say that you jump off a porch and you're falling really fast by the time you get to the ground. If you hit the ground with your legs straight, you're going to stop essentially instantaneously. Which means, let me put it in a formula. If you keep your legs straight and you hold them straight, the time it takes you to stop is a very small time. Your change in momentum has to be the same no matter what. You have to go from some speed to zero. You can't change your mass. But if the time is small, that means the force that's causing that change has to be huge. So big that it might break your bones. But on the other hand, let's say you're smart enough to know that when you jump from a high distance like that, you need to hit, and as you're stopping, you're bending your legs. Well, that makes this time be much bigger, the stopping time much bigger, which means the force required can be much smaller. So you can do that without being injured. It's the way airbags work. If you hit a wall in your car, moving very fast, this has to change the same no matter what. What an airbag does, when you hit an airbag, instead of hitting your steering wheel, the airbag slowly compresses. The time it takes you to stop becomes fairly large, and therefore the force that's stopping you is fairly small. That way you don't break your neck. Cushions work the same way. Cushions slowly stop you. They increase the time it takes for you to stop, thereby decreasing the force that's required to stop. The opposite could be said, though. Let's say you're hitting a golf ball or hitting a baseball. every good coach of golf or baseball tells you that one thing you need to do is follow through on your swing. When you're hitting a ball, if you follow through, the amount of time that your bat or your club is in contact with a ball becomes very large. Let's say you don't change the force. If the time the ball is in contact with the ball, if the time the bat or the club is in contact with the ball goes up, the force stays the same, that means something on this side has to give. You can't change the mass of the ball by hitting it, but what you can do is you can make it go faster. So if you follow through, your bat or club touch the ball for longer, therefore the ball is going to leave that bat or club with a much higher change in velocity. It's going to be going faster, therefore it's going to go further. That's impulse momentum theory. One of the main types of problems we're going to work in this chapter is dealing with impulse and momentum theory. And we'll see some of those problems here in just a second. Another thing that we want to talk about is the law of conservation of momentum. That essentially says that the momentum that a closed system has at the beginning is the same as the momentum it's going to have at the end. Now, for that to be true, we have to be dealing with an isolated system where there's nothing coming in or out of the system. We're going to talk about three kinds of collisions real quick before we work any problems with conservation of momentum. And the first kind of collision we'll talk about is an elastic collision. This is where objects collide and they bounce off of each other. Momentum is always conserved in collisions. It's always conserved. A lot of the problems that we'll work with momentum, though, are going to be perfectly elastic collisions. And these are where two things collide and they bounce off and there's no energy lost. So essentially the momentum and the kinetic energy are both conserved. The momentum you started with is the momentum you end with. The kinetic energy you started the problem with is the kinetic energy you end the system with. The other kind of collision, though, is inelastic. And these are where two objects collide and they stick together. Well, as they're sticking and they're deforming around each other, there's some friction that's happening. So some energy is lost. Momentum is still conserved in these collisions. Kinetic energy is not. The kinetic energy usually is going to decrease. So that being said, we're going to work two kinds of problems. The problems are either going to be impulse momentum problems or they're going to be conservation of momentum problems. That the momentum before has to equal the momentum after. Let's work on conservation of momentum problem to begin with. Let's start off with one like the first one here. A 100-kilogram man is standing up on the seat of a 33-kilogram cart. It's a big cart, by the way. The cart and the man are traveling at a velocity of 25 meters per second. The man then jumps off the front of the cart and hits the ground with a velocity of 32 meters per second in the same direction as he and the cart were originally traveling. Calculate the velocity of the cart after the man jumps off. Okay, so let's say the man and the cart are going this way. The guy's going to jump off the front of the cart. He's going to jump off this way and continue to go. For him to jump forward, he has to push the cart backward, right? So our idea here first is going to be momentum before equals momentum after. This is a conservation momentum problem. So let's think about the momentum before. In the beginning of this problem, we have a 100-kilogram man and a 300-kilogram cart. 400 kilograms. That's the mass. Remember that momentum is mass times velocity. So we've got 400 kilograms of mass moving at 25 meters per second. So the momentum at the beginning of this problem is 400 times 25. Well, that's got to be equal to the momentum at the end of this problem. Well, at the end of the problem, we have a 100-kilogram man moving at a velocity of 32 meters per second. But we also have the cart. We know the cart is 300 kilograms. But what we don't know about the cart is how fast it's going, and that's what we're trying to find. So we're going to say the mass at the beginning times the velocity at the beginning. It's the momentum at the beginning. That has to equal to the momentum after. Mass times velocity plus mass times velocity. We're going to solve this for V. So we're going to go 400 times 25. 400 times 25. And we end up with, that's 10,000. So we're going to end up with 10,000 kilogram meters per second equal to 100 times 32. So 3,200 kilogram meters per second plus 300 times V. So let's subtract the 3,200 from both sides. That gives us 6,800 equal to 300 kilograms times V. Divide both sides by 300. And we end up with a velocity of 22.7 meters per second. And it's positive 22.7, which tells us that that cart continues to go forward. Now, there are cases where this number might come up to be negative. And if it came up to be negative, that would tell us the cart's going backwards from its original position. Our answer to 1B, will the cart keep moving in the same direction that it was initially moving, or will it begin to move backwards? And our answer here is it's going to keep moving the same direction, it's just going to be going a little bit slower. If we want to do C, calculate the change in kinetic energy for the system. Let's write down our velocity numbers for a second. Our cart at the end of this problem, we'll say velocity of cart is 22.7. The velocity of the man at the end of this problem was, let's see, 32 meters per second. Do a little erasing here. Remember that when we want to find the change in anything, we usually take the final minus the initial. Also remember that to calculate kinetic energy, we're going to use the formula 1/2 mass times velocity squared. 1/2 can be squared. So, let's calculate the kinetic energy at the beginning of the problem, before the guy jumped off. 1/2. The mass in the beginning, the man and the cart were together, so 400 times their velocity squared. They were going 25 meters per second. So let's go 25 squared times 400 times 1/2. We end up with a kinetic energy, we'll call this kinetic energy initial, 125,000 joules. Well, the kinetic energy at the end, we need to calculate the cart's and the man's kinetic energy separately. So let's do the cart first. 1/2. The mass of the cart is 300 kilograms. At the end of this problem, the cart is going 22.7 meters per second. I've got to square that. 1/2 mv squared. So the kinetic energy of the cart, the final kinetic energy of the cart, we'll call that KEFC, is 77,293.5 joules. All right, now let's calculate the kinetic energy of the man. 1/2. Mass of the guy is 100 times the velocity squared. He was going 32 meters per second. So 32 squared times 100 times 1/2. The kinetic energy of the guy at the end of the problem is 51,200 joules. So our final kinetic energy is going to be the final kinetic energy of the car plus the final kinetic energy of the man. Let's add those two together. 51,200 plus 77,293.5. So we end up with a final kinetic energy of this. 128,493.5 joules. All right, but we started off with 125,000 joules. And we've got more kinetic energy at the end than we had at the beginning. If you want to calculate the change in that, just subtract it. And you might be thinking, how did that happen? Well, to jump off the cart, the guy had to push, which means the guy was doing work. And you guys know that work can be equal to a change in kinetic energy. So because this guy did some work, the kinetic energy increased. All right, let's go ahead and work a problem like number 2 here, which is more of an impulse momentum problem. A 300 kilogram truck is moving down the street at a velocity of 16 meters per second. How long will it take for an 800 Newton braking force to stop the truck? Remember, from Newton's second law, we derived this equation. Impulse momentum. A force can either cause a change, a force causes a change in momentum. And in this case, we're trying to stop the car. We're looking for the time it takes to stop. So if we take that equation and we solve it for time, we can see that delta t is equal to m delta v divided by the stopping force. So we'll take our 3,000 kilogram truck, the mass. The velocity's got to change from 16 to 0. So our change in velocity is going to be 0 minus 16, final minus initial, negative 16 meters per second. It's our change in velocity divided by our force. Our force is 800 newtons, but it's a braking force, which means it's opposite of the direction of motion. So we're going to put a negative on that as well. The force is in the opposite direction that the car is moving. So let's go 300 times negative 16 divided by 800, and we end up with 6. And if you look at your units, you're going to end up seeing that this change in time is 6 seconds. It's going to take this braking force 6 seconds to stop that car. Apparently those brakes are not very good. Those are the 2 main examples of problems that you're going to see. I'm going to stop there, and the substitute will give you some sample problems. We'll talk more about these on Tuesday.